All right, so for today, topic's discrete binary search. It's a little trickier of an application to binary search, but just in case, like some people weren't as familiar with binary search, I was gonna go over the regular one anyways. So essentially, like for binary search, it's a faster way to find an array or an element in an array. What if this is our given array and we want to find like 15, we could just start at the beginning, go all the way to end, and then check if we have it. But a property of a sorted array means that like for example, like let's say like we want to look for the number 4. If like I check 5, then there's no point in checking everything on the right because everything on the right is bigger than 5 or bigger than 5. So 4 can't possibly be on the right side of 5. So I'll just walk us through a quick little like binary search example. So what we're gonna do is we're gonna have two pointers, a left and a right, and let's look for 10. So like our desired value x is equal to 10. So I start our right pointer over here, or our left over there, our right over there. What we're gonna do is we're gonna take their midpoint. And in the case that like the segment is of even length, I'll denote the one on the left to be the midpoint. So these two are endpoints. We want to take the middle, so the middle's right here. Is 5 equal to 10? No, it's not. It is less, so that means we can disregard everything on the left. So a 5, so I'm gonna move our pointer one over to the right of our midpoint. So this pointer moves all the way over here. So I'll move this to here. Calculate our new midpoint. Our new midpoint is 12. 12 is not 10, it is greater, which means that we don't care about anything on the right of it. So I'm gonna move our mid or our right pointer to one left of our old midpoint. So now our right pointer is gonna move all the way over here. And then now we've reached 10. 10 is equal to 10, so we found it. So instead of doing one check for every number in the array, we found 10 in only 3 operations. And generally speaking, the time complexity of a binary search will be O of log base 2 of n. Um, Now the part where discrete binary search comes into play is that we can use binary search for more than just finding elements in an array. So the way that you should be thinking of binary search is if you have some monotonic function, then you're able to binary search the answer. So what a monotonic function is it means like if it means that like you're gonna be like increasing towards a certain value and then decreasing after. And if we instead think of like this binary search as looking for 10, and instead change it into looking for an index such that, let's call this array A. So we want an index A such that A sub I is less than or equal to 10, and we want to find the last index for which that's true, then our answer will be right here. Does that make sense? So like for example, 1 is less than 10, right? So this would also be true. This would be true, this would be true, this would be true, this would be true, and then these two are not less than 10, so these would be false. So if I were to label them in trues and falses, we would get true, 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 false, false. And then now what we're binary searching over is the last index such that um this condition is true. Um, so using this thought process, we can expand binary search to instead solve some more complicated problems. So I have to look over to like what my test cases are for this problem. So let's say let's say we have a problem where you you want to produce a certain amount of like a product, so like in the problem I wrote is just called suits, and you have a bunch of machines that simultaneously produce suits at different rates. So x you want to make x equals 18 suits, and then you also have four machines that produce at different rates. So the first machine produces at one suit per minute. The next one is or wait, three. It's actually the other way around. So it takes 1 minute to produce a suit. Um, the next machine is 3 minutes to produce a suit, and then 2, and then 7. So granted that you have these machines, then we want to find the minimum amount of time that we need to make 18 suits. So to give you an example, let's say we let 10 seconds pass by. So if 10 seconds pass by, then from this first machine we're gonna get 10 suits because it makes or not seconds, I chose minutes. So from this first machine, we're gonna get 10 suits because it takes 1 minute to make one. So by 10 minutes, we'll have 10 of them. The second one can make 3 suits within 10 minutes, so plus 3. This one over here will make 5 suits in 10 minutes if it takes 2 minutes to make just one, so plus 5. And then this last one, if it takes 7 minutes to make a single suit and we have 10 minutes, then it'll only be able to make one. So in 10 minutes, we have 10 plus 3 plus 5 plus 1 suits, which is 19 suits. And I think I arbitrarily chose that value, and that's actually the answer. So the minimum amount of time needed to get 18 suits would be to try 10 minutes. I'm gonna go ahead and try it for a different number just so we can see what would happen. So if we let 14 minutes pass by, we would get 14 plus 4 plus 7 plus 2, and then we would have 27 suits, which is more than we need. But what if instead we only let 5 seconds pass? Then we would get 5 plus 1 plus 2 plus 0. Like, this is how many numbers each of the machines would produce. And then in 5 minutes, we would only get 8 suits produced. So the observation that we can make is this is what we could call a monotonically increasing function, right? So if I go ahead and choose all of the times, so like I'll these are all of the times in minutes. So if we know that the minimum amount of time to make 18 suits is 10 minutes, then I'll say this is true. So in 10 minutes we can make 18 suits. Then that must mean that in 11 minutes we'll also have 11 if not more suits. And this is true for every single number above 10. Whereas at 9 minutes, where we don't have enough suits to have 18 yet, right? Like in 9 minutes, we'll have 9 plus 3 plus 4 plus 1, which will be 17. So 9 minutes is not enough time to make 18 suits, so this would be false. And then it's implied that it doesn't work for any time less than that, right? So these would be falses all the way through. So now that we know that this is a monotonically increasing function, what we can do is something called binary searching the answer. So instead of like brute force simulating like does it work in 1 minute, does it work in 2 minutes, 3, 4, 5, all the way until like I don't know, like possibly 10 to the ninth minutes, we can binary search this space to find the first time um or the smallest time such that we have 18 suits. So the way this is going to work is you can kind of take it as like a regular binary search, where instead of our condition of like trying to find a number, our condition is now checking if we can make 18 suits in that time period. So like if I go ahead and like do an example right here, our two pointers start at 1 and 14. Let's just say that 14 is the maximum amount of time that we know we can complete an answer in. Most of the time, you're gonna have to look at the constraints, and you're gonna set your upper bound to be equal to the biggest number in the input. So I usually choose like 10 to the 18th to be sure. And the reason that work is even though 10 to the 18th is a really big number, you're binary searching um on that range. So you're only gonna be doing log base 2 of 10 to the 18th operations, which would just be like 60 or something operations. So if we do a binary search on this, we first have to find our midpoint, so I'll just choose it to be 7. Can we make enough suits in 7 minutes? Well, we already know the answer is 10, so we can't. which means that everything on the left also cannot be made uh, everything on the left cannot make 18 seconds or 18 suits in time. Therefore, I'm going to move our left pointer to one past our midpoint. So this is going to move all the way over here. And then now we're going to look for a new midpoint. So now we try this midpoint right here. Is 11 seconds enough to make 18 suits? In this case, we know that it is. So we know that everything on the right will also work, so there's no point in checking those. So we're going to move our right pointer over to here. So now we have 8 and 10. And an important point is when you find something that works, you're going to want to set your answer to it just to save it, and you'll just overwrite it later in case you find a better answer. So in this case, to the best of our knowledge, in 11 seconds we can make enough suits, or I keep switching between minutes and seconds, but 11 minutes we can make enough suits. So for now, we're gonna save this as the answer and see if we can find a better one. So now our pointers are at 8 and 10, so the midpoint is 9. Is 9 enough time to make 18? No, it's not. So I'll move our left pointer to one past the middle. So now both pointers are at 10. Is 10 seconds enough? Yes, it is. So now I'll update our answer to be equal to 10. And then by now the pointers are on top of each other, so the binary search would terminate. And now we've been able to deduce that the solution is 10, and we've done a binary search over it. So instead of having to brute force check every single time to see if it works, we're able to solve it in log n. So that's basically the example I want to go over. I have some other ones that I'll show on my computer, but I won't be going as in depth. I just want to show like kind of like the types of problems that you can solve with it. So are you all good on that, Paul?
Yeah.
Sick. So let's see. So I'll just go over like two other problems that you can solve these with. So I can't see what I'm sharing, but I'm sharing like you can see Cody, right?
Yeah.
Oh wait, let me drag OBS out. So so here's two problems that you can solve with it. So what we do here is usually binary search problems are very hidden. It's usually very hard to make the observation that like you can binary search over the answer. So let's say we have this problem, right? Where you have a square of size n by m. So you just have a grid. You start at the bottom left corner, you want to get to the top right corner, and there's a bunch of people standing in the way, and you want to get to the end in such a way that you stay as far from people as possible. Also, since I'm in streamer mode, I didn't hear Giannis join. How long have you been here? Long enough?
I've been here for about 15 minutes.
Oh, okay, that's good. I wasn't sure if you were on the whiteboard. Okay, so basically for this example, you want to find a way to the end, and you want to stay as far as possible from like anyone as you can, right? So at first it's really hard, right? Because like how can you make a path like that limits how like how do you know like how far you're gonna get from people, and you're gonna try to do all this weird stuff. But what the solution is to treat each person as a circle, and you're gonna binary search each of the radii. So what you're gonna do is you're gonna assume each person has a radius of like 1 or something, and then you're gonna try all the way up until like 10 to the ninth, and you're gonna say like, okay, like assuming that like these people can reach this far, like can I reach the end? And the answer is gonna be the biggest radii in which you can still reach the end. So I'll go ahead and like do it over paint, but like what's gonna happen is like if we have like start end here, and then you have like person here, person here, person here. You're going to check for different radii. So you're gonna say like, okay, like let's try like a radii like this small, and then you're gonna notice you can make it to the goal still, right? So then you're gonna try to up the radii, and then maybe you'll make it too big to where it's like this, right? And you're gonna be like, okay, I can't make it there, so I have to try a smaller radii. And then when you find a radii that's just perfect, like you can barely squeeze through here, then that's your answer, right? That's as far or that's the furthest distance that you can get from anyone and still make it to the goal. So this is a really advanced problem, but it is binary searchable. And then this other example, you'll notice it's literally tagged as hard on this website because these types of problems usually aren't too easy, but at least you have the tool to use it, right? So let's say you want to um you want to like split this array into k different sublists, and you want to make the sum as small as possible. So what happens here is k is equal to 2, so we can put these into two like contiguous containers, but we want the sum to be as small as possible. So what the answer in this case is 10, because if we put the first 4 in one container and we put the 9 in its own container, then the sum of this one is 10 and the sum of this one is 9. So the minimum largest sum across the containers is just 10. Does the problem make sense?
Yeah.
So like let's say k was 3, then I don't know. I'm sure the answer is 9 for k is equal to 3. But like if k was 3, like you could try putting like these in one container, these in one container, and then this in its own container, and the answer would be 9. Because like the 9 would be the biggest sum out of all containers. So this is a very pretty like typical like common binary search problem. And what you're gonna do is you're gonna binary search for the sum. So what you're gonna do is you're gonna say, okay, I'm going to assume that my container cannot exceed this sum. Can I still get it done in k containers? And if you can't, then you have to try a bigger sum size. Otherwise, you're gonna try to find a better answer and go smaller. So in this case, right? So 1, 3, 2, 4, 9. The answer is 10, but let's say we tried 8, right? So let's try to see if we can have our maximum sum be 8 and fit it in two containers. Well, if we try 8, we can fit this in one container, this in one container, and then this can't fit in any container, right? Like it's too big. So like this simply wouldn't work. So now let's try 9. So you could fit these in one container, this in one container, and this in one container. But you'll notice we're only allowed to break it into two containers, right? And here we've done 3. Therefore, 9 doesn't work, so we have to try a bigger sum size, right? So now let's say we try uh let's try like 12, right? So if we try 12, then I can fit all of these in one container because this is 10, and I can fit this, which is just 9. So we know that 12 works, right? But since 12 works, we should try to find a better answer, right? And look towards the smaller container sizes. So when we finally try 10, um, we'll see that it's the smallest answer that works. So if I were to draw this out to like mimic like the true and false like thing I was doing earlier, this would be false, that would be false, this would be true, and then all of these would be true, right? So you can fit, if you have a sum of any of these values, you can fit them into either k or less. So like you can fit it in k or less containers, right? So your goal with binary search is to try the first index that is true. So that's how you're going to be using binary to solve this problem. Of course, this is a harder application of binary search, but I just wanted you to get an idea of what you can use it to
Do you
solve.
store all of the sums to 10 to the ninth?
Like my search range, yeah. See, so I just call it
Okay.
infinity, but like I'm just assuming that the sum can never be more than 10 to the ninth, right? So I'm gonna try every answer and hope that it's between 0 and 10 to the ninth. Like I said, this number usually depends on your constraints. So what I usually do is I just use long and then set this to like 10 to the 18th and it'll work out. Most of the time, especially on sites like binary search, it's going to be an integer, so you don't have to worry about that. So for the problems I made for you guys today, signed out. Um, this first problem, you're going to be given an array, and you're going to find the rightmost element that is less than or equal to x. And your answer will be one indexed. So in this example, this is your array, and you want to find the index of the rightmost number that is less than or equal to 4. So the answer is 2, right? Or this number right here. Because if we go to this one on 5, it's greater than 4, so it doesn't satisfy our condition. So our answer is 2. For the next one, you want to find the rightmost element that's less than or equal to 8, and that will be this 8 right here, right? So 1, 2, 3, 4, 5. It's index 5, so the answer is 5. And then for the last one, you want to find the rightmost element that's less than or equal to 9. It's you have two nines right here, right? But you want to find the rightmost element. Therefore, the answer will be the index all the way over here, the righter 9, which will be index 7. So the answer is 7. So that's this first problem. The second problem, you're going to be given a number n, and you want to find what's the square root of the number rounded down without using the square root function. So so for example, the square root of 40 is like 6 point something, but if you round it down, the answer is 6. So in essence, I'm asking you, what is the biggest number such that if you square it, it's less than n, correct? Because 6 squared is 36, which is less than 4. 5 squared is 25, which is less than 29. 6 squared is 36 again, less than 44. And then for this last one, for example, what's the biggest number that if you square it, it's still less than 7? Well, it's going to be 2, because if you pick 3, 3 squared is 9, so it wouldn't work. So that's how this problem works. And then this suit problem is the one I went over on the board, and this last one's just a challenge problem. So yeah, I'll give you guys about an hour to work on it, and then we'll go over solutions at 3:30. Any questions before I let you guys loose?
Nope, looks good.
All right, sick. And as always, if you need any help, just call me over and I'll help walk you through them.
All right.
Thank you for